9.2.3, minimum or maximum value. So a minimum point on a graph is the point where the smallest output value, and that output value is called the minimum value. Now, not all graphs of functions have a minimum point. So if we think of like a linear function, there's no minimum point because there is no lowest point on the graph. But quadratic functions that open up right here at its vertex, this will also be a minimum point. Okay. We'll have, again, it has its lowest value here at its vertex. And a maximum point on a graph is the point with the largest output, and that output value is called the maximum point. That should say maximum value. And again, not all graphs have a maximum point. Again, if we think about the linear functions that we looked at, again, this has no maximum either. It keeps going up, 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 up forever. But if a quadratic function opens down, then this vertex will be a maximum point. We'll have our outputs increase, increase, increase to this maximum value, and then they'll start to decrease again. So example 7 says the revenue function for a company can be modeled with this equation. Okay, so this one we should recognize is quadratic. It has our necessary x squared term in it, and then optional x or constant terms are okay. And the cost function can be modeled with this equation, which we should recognize as linear because it has just x terms and constant terms, where x is the number of items made and sold each day, and cost and revenue are in dollars. So the first thing we're asked to do is to find the profit function. And they've given us a hint here where profit is, the total amount of money you take in minus all the money that you had to pay out. So our profit function would be revenue, so this whole quantity, 6x minus 0.02x squared, minus this whole quantity. So we need to be careful so that we do distribute the negative through. Okay, here there's nothing, positive 1 if we want to think about it. If we distribute, we're just going to get 6x minus 0.02x squared minus 100 minus 2.4x. And so if we combine like terms, we're going to get px, and I'm also going to write these with the x squared term first. So negative 0.02x squared, and then we have a positive 6x minus 2.4x, so we'll get a positive 3.6x, and then our constant term, minus 100. And so here is our profit function. So now we're asked to find the coordinates of the vertex using the vertex formula. So for the vertex formula, we need the 3 coefficients. So the coefficient on x squared was negative 0.02, coefficient on b was 3.6, and coefficient or a constant term was negative 100. So the opposite of b over 2a, we get the opposite of 3.6 over 2 times negative 0.02. So we'll get negative 3.6 over negative 0.04. And if we divide, we get 90. Okay, so this is the x coordinate of the vertex. And again, to get the y coordinate, the output, we need to put this through our profit function. So we'll take p of 90, negative 0.02, and again, before we substitute for x, we're going to put parentheses around the variable. And so if we evaluate, that should say 100. So now, if we evaluate that expression on the right-hand side, all right, so computer's flipping out here. All right, so if we evaluate this expression, we get 62. So for an input of 90, where x was the items made per day, we get an output of 62, which was in dollars, and this was $62, and that was profit. So if we explain what this means in the context of this problem, that tells us that if they produce 90 items per day, they will make a profit of $62. Okay. So what that means on our graph is that right here at 90 is where we reach the maximum profit of 62. So if this company is currently producing 100 items per day, should they increase production or decrease production to maximize profit? So we just figured out that to maximize profit, they need to make 90 items per day. So if they are currently making 100, they need to decrease production. So they should decrease production, and specifically they should decrease it to 90 items per day. So let's see what happens right now. Their profit, as they're making 100 items per day, if we stick that through our profit function, we get an expression that looks like this. Oh, I cannot write the number 100. There we go. And if we evaluate this, we get $60. Okay, that points over here somewhere at 100, and the profit's only 60. Okay, the profit's bigger if they only make 90. So again, company to make more items, sometimes that means that they have to, pay overtime to workers and so on, and then it's not as profitable. So in this case, they should decrease production to 90 items per day. All right, so our last example for this section. Okay, looking at some real-world data. So we've got the average number of viewers of CNBC's Business News are listed in the following table. So these are the years and the collected data in thousands of viewers. And we're going to let T be years since 2000. So we're going to subtract 2000 from all of these. So we're going to get 0, 2, 4, 6, and 7. And we're going to put this in L1 and put this in L2. And then we can push second function, y equal, to get into the stat plot so that we can make a scatter diagram of the data. We tell it what list to look at, and then we're going to push zoom 9. So we would get a graph that looks something like this. So we've got some points on here that look like that. So from the scatter diagram, does it look like a linear model or a quadratic model would fit better? And in this case, a linear model, we would need something that looks like this or this, which doesn't fit our data very well. Where a quadratic model, we can look at something that has this bend or curve to it. So now we're asked to graph this given equation. So we're going to push y equals, and we're going to enter 10x squared minus 84.16x plus 364. And again, we're going to use zoom 9 so that it puts it right on top of, we'll see, right on top of, and it fits those points in our scatter plot really, really well. So now we're asked to compute the estimated viewers if the input is 13. So if we put that through our function, again, remembering to put parentheses around each variable before we substitute. And if we do that, we evaluate this expression, we get 959.92. So if we interpret this in context, the input here is years since 2000. So in 2013, and then the hat is an estimated or predicted value, so we estimate that the number of viewers per day for this, what did we have, CNBC, okay, is 959.92 thousand. So now we're asked to estimate when that average number of viewers was at a minimum. And I guess that word belongs in here too. This was the average number of viewers over the course of the year. So now we want to know when that was at a minimum. Okay, so again, this is going to happen at the vertex. Okay, so we want to know where this vertex, where it bottoms out at that lowest value. So we're going to use the vertex formula. So the x-coordinate of the vertex is the opposite of b over 2a. So let's see, so for this one, our a was 10, and let's see, b was equal to negative 84.16, coefficient on x squared, coefficient on x, and our constant term was 364. So the opposite of b, all over 2 times a, so we would get 84.16 divided by 20, which gives us 4.208. And then to get the y-coordinate, we would put that through our function. So we plug this into our function, and we would get about 186.9. Okay. So again, if we interpret this, that tells us, about 4.2 years after 2000. Again, we estimate the average number of viewers per day is 186.9 thousand.